Good morning, students. Our today's topic is relation matrix and properties of relation. So today's we have to check whether the relation matrix holds the relation properties or not. With the help of a table formed by like this, we can check easily the given relation matrix is reflexive, symmetric, transitive, or etc. Here, our first example is one matrix of 1 0 1 0 1 0 1 0 1. This is the first matrix relation. Since all the elements of the diagonal elements are 1, so this is reflexive. The rules by which we check the relation properties, I am sending you. You can see there. And here we try to how you apply the properties of relation, how we check. So since all the elements are diagonal elements are 1, so this is reflexive. And if all the diagonal elements are 0, then it is irreflexive. Here all the elements are 1, so this is not irreflexive. And whether symmetric or not, if the transpose of the given relation matrix is the same as the given matrix, that means transpose of this matrix is also equal to this, then the matrix is said to be symmetric. So since here transpose of this is equal to the given matrix, so this is symmetric. And now check whether antisymmetric or not. If the elements diagonally image of 1 equal to 0, then the matrix is said to be antisymmetric, or non-diagonal elements are 0. Here the diagonal element 1, 1. So the image of 1 is not equal to 0, so this is not antisymmetric. Now complement. How you write the complement of the given matrix? We change 1 by 0, 0 by 1. So write 0 for 1 and 1 for 0 and 0 for 1. And next 1 for 0, 0 for 1 and 1 for 0. And here 0 for 1 and 1 for 0 and 0 for 1. And inverse of the matrix is the transpose of the matrix given. So the matrix, and since this is symmetric, so the inverse of the matrix is the same as the given matrix. 0 1 0 1 0 1. Now example second. Since not all the diagonal elements are 1, so this is not reflexive. Also not the diagonal elements are 1, so this is also since all the diagonal elements are not 0, so this is not irreflexive. And symmetric is since diagonal of this transpose of this matrix is not the equal to of this, so this is not symmetric. And now check whether this is antisymmetric or not. Since image of one diagonally equal to 0, diagonally image of 1 equal to 0, 1 diagonally 0, so this is clearly antisymmetric. If the elements of one diagonally is 0, then the matrix is antisymmetric. Or we can check non-diagonal elements are equal to 0. Now complement of this. Complement of this is easy. 0 replaced by 1, 1 by 0. So 1 and 1, here 1, this is 0, 0, and this is 1 and 1. And now transpose of this 0, 0, 0, 1, 1, 1, and 0, 0, 0. This is the transpose of this matrix. So this is the inverse of the matrix given. Now see the third example. Since all the diagonal elements are not 1, so this is not reflexive. And since all the diagonal elements are not 0, so this is also not irreflexive. Now symmetric or not? Since clearly the transpose of this matrix is same as this, so this is symmetric. And antisymmetric, one diagonally, the image of diagonally 1 is not equal to 0, so this is not antisymmetric. And now write the complement of this. Replace 0 by 1 and 1 by 0. 0, 0, 0, 0, 1, 0, and 0, 0, 0. This is the complement of the given matrix. And now the inverse of the matrix, since this is symmetric matrix, so the inverse of the matrix is the same of the given matrix. So 1, 0, 1, 1, 1, 1, like this. And now last example is fourth example is here. Since all the diagonal elements are 0, so this is irreflexive. Not equal to 1, not diagonal elements are equal to 1, so this is not reflexive. And since its transpose is not equal to this, so this is not symmetric. And now check whether it is antisymmetric or not. Since here diagonally we can see here image of 1 equal to 0 and 1, image of 1 0 and 1 0. So diagonally the image of 1 equal to 0, so this is antisymmetric. And now write the complement of this matrix. Write replace 0 by 1 and 0 or 1 by 0. So we get 1, 1, 0, 0, 1, 0, 1, 1, 1. And transpose of this is the inverse of the given matrix. So write here transpose of the given matrix 0, 1, 0, 0, 0, 0, and 1, 1, 0. And the given relation matrix is whether transitive or not, we can check like the normal relation. If xy belongs to R, yz belongs to R, then xz belongs to R. If if we obtain like this, then the given relation matrix is transitive. So transitive relation is checked by same process as the normal relation. Now we have another question. What is the composition relation, composition of two relations R is equal to 2 4 7 7 4 and 9 2, and S is equal to 2 9 and 7 4, and next 4 2 and last 7 9. How can we write its composition? First ROS and second SOR. How? That means composition relation of SOR is denoted by ROS. So we read here in inverse order. Not this is the composition of relation SOR, this is the composition relation of SOR, not ROS. So how can we write the composition relation? What is the member of this relation? How can we obtain? So this is ROS is the composition relation of SOR. So write here the domain of S first, and domain of S is equal to 2 7 4, this 2 4 7 2 4 7 and 9. Write the all elements 2 4 7 9, and also we can write 2 4 7 is the element here, so we can write 2 4 7. Also here write 2 4 7, since here only we have the elements 2 4 7 in all. Also write here 2 4 7 and 9, and this is the composition relation of SOR. So write S first and R next. Now we first the elements of S is directed by the directed rays. First here at the elements of S is 2 9. So 2 is connected with 9. 2 is connected with 9 like this, and 7 is connected to 4. 7 is connected to 4, and 4 is connected to 2. 4 is connected to 2, and next 7 is connected to 9. 7 is connected to 9 here like this. And now R. Here the relation R. R is the element of R is 2, 2. So 2 is connected to 2. 4, 7. So 4 is connected to 7. And 7 to 4. 7 to 4. And 9 to 2. 9 to 2. So how can we write the composition relation SOR, which is the member of ROS? That means composition relation of SOR is equal to like this. 2. First we say that 2 is connected where, and lastly which connected to by which element. So 2 to 9 and 9 to 2. So write 2, 2. So 2 is finally connected to 2. And then 4. 4 is connected to 2 first and 2 is connected to 2. So 4, 2, write 4, 2. And now 7. 7 is connected to 4 first and then 7. So write here 7, 7. And next 7, 7. And 7 4. And 7 is also connected to 9 first and 9 is 2. So 7, 2, write 7, 2 also. 7, 2. So ROS is like we obtained. And now SOR. So first we write the element here 2, and 2 is finally connected to which element we can see here. And write the composition, which is the member of the composition relation ROS. Now we write similarly the relation SOR. How can we write this? SOR like this, all the elements are 2 to 9. So write 2, 4, 7 and 9. This is the all elements. So like write this 4, 7 and 9. Also write here 2, 4, 7 and 9. And this is SOR, so write R first and S second. So we write the element of R with connected rays. So element of R is 2, 2. So 2 is connected.